Hi, I'm Mrs. Burns, and welcome to Lecture 2 of our Chapter 7 unit. Today we're going to talk about alpha, beta, and gamma decay. So we've already talked about radiation. So radiation is simply, radiation refers to high energy rays or particles emitted by a radioactive source. So when the nucleus of an atom is unstable, it will undergo radioactive decay. So awesome guy Ernest Rutherford experimented with radioactive decay. He discovered that there are 3 common types of radiation emitted. So what he did was he isolated some sort of radioactive source here, and he stuck it inside a lead block so that that radioactivity can't go everywhere. But then in that lead block, he just had a little hole, and so he allowed the radiation to go out that hole. And then after the hole, you see here, he put a positive plate and a negative plate. So because the plates are charged, any charged particles will either be repelled or attracted to the different charged plates. So the negatively charged beta particles were attracted to the positive plate and also repelled by the negative plate. So they went up here. The positively charged alpha particles were attracted to the negative plate down here. And the uncharged gamma particles were not attracted or repelled by the charged plates. They just went right through the middle. So, that led him to discover these 3 common types, and let's look at them a little bit further. Alpha particles are relatively large atomic particles. Relatively just means compared to the other ones. That is beta and gamma. So they're relatively large, and they're released during alpha radiation. And because the nucleus has the same combination of particles as a helium atom, you can write it as either 4-2 alpha, 4-2 helium. So this means that it has a mass number of 4, which we see up here, and an atomic number of 2, which we see down here. And so that means it has 2 protons, and since the mass is 4, that must mean it has 2 neutrons as well. 2 protons means that it has a charge of 2 plus, or plus 2, and a high mass means that it is relatively slow moving compared to the other 2. If something is heavier, it doesn't move as easily. It cannot penetrate even a sheet of paper. So it cannot penetrate very much. So it will definitely get blocked by concrete. It will definitely get blocked by aluminum foil, and it will also get blocked by paper. So when alpha particles leave the nucleus of an atom, this is called alpha decay. And when we write a reaction when this happens, we must remember that it needs to stay balanced on either side. Now we're not going to be balancing the same way. We're going to be balancing a little bit differently. Just checking out the mass numbers and the atomic numbers, that everything stays equal even though it gets divided up a little bit differently. So let's take an example here for alpha decay. If we have 208 as our mass and 84, and we have polonium. And if this undergoes alpha decay, then we get something plus our alpha particles here. So we know that whatever we have here for our mass and atomic numbers, that it has to be equal on one side versus the other side of this arrow, this reaction sign. So we can just do some simple math here. 208 minus 4 is 204, and 84 minus 2 is 82. So our mass has gone down and our atomic number has gone down. Now, if the atomic number goes down here from 84 down to 82, it's no longer the same element. Take a look at your periodic table in your textbook or in your data booklet, and you'll see that 82 does not belong to polonium. 82 is the atomic number that belongs to lead. So here we have an 84 to 82 atomic number. I'm just going to write down for decrease. And this went 2 changes left. So it went 2 to the left because it went down from 84, 83, 82, 2 changes. So that was an atomic number decrease. Now, when we have beta radiation, the mass of a beta particle is so low that we basically consider it zero. It's negligible. It means that it doesn't really count. This makes sense because beta particles are electrons, and we know that electrons compared to protons and neutrons have a negligible mass, basically nothing relative to the others. Beta particles have a charge of 1 minus or negative 1, and they can be written as either atomic mass of 0, negative 1 here because they're not on the periodic table, and this is the same for electrons. Fun facts for beta. Low mass means that they're relatively fast moving, faster than alpha particles at least. They have a greater penetrating power than alpha particles. That means that they will go through that piece of paper that alpha particles get stopped by, but they cannot go very far because they are stopped by a thin sheet of aluminum foil. That's just aluminum foil. That's just the stuff that you use to keep your chicken warm. So when beta decay occurs, the neutron is actually being changed into a proton and an electron. And the proton stays put in the nucleus, and the electron goes, and it shoots out super high energy, and it just goes for it. So now we have in the nucleus one extra proton. So what is going to happen to the atomic number? Think, if you have another proton, is it going to go up or down? If you said increases, it goes up. I'm very pleased. So the atomic number increases because we have another proton, so it changes to a higher element on the periodic table, one number up. The mass number does not change, however, because protons and neutrons are about the same, and losing an electron is like losing no mass, so no big deal. So let's try an example. The example that I have for us today is carbon 14 undergoes beta decay and becomes something plus that beta particle. So if we know that the mass number doesn't change, then it must stay 14. But the atomic number increases, and in this case we just have one beta particle, so it's just going to increase by 1 here. So now we have 7. Now what is the element in the periodic table that has an atomic number of 7? If you look it up, you'll see that it's nitrogen. So here, if we just want to write this, 6 to 7 becomes nitrogen. So this is very helpful to know your periodic table. Last but not least, gamma radiation. So gamma particles are high energy, and they are short wavelength. So that means that they're waves like this, really close together, as opposed to the long and lazy ones. So they're really short and quick wavelengths. There is almost no mass and no charge to the radiation, so it doesn't change the atomic mass or the atomic number of the atom. So that's kind of weird, right? You're probably wondering, well, what does it even do? Well, I'll tell you in a second. Gamma radiation is represented by 00 gamma. It is the highest frequency and highest energy of all radiation, and it's the most dangerous. If you look at that electromagnetic spectrum, which goes from left to right, and it's like long and lazy, and then it gets really fast, and we've got this like little area of visible light, gamma radiation is over here. It's super high energy, super high frequency, super short wavelength, very dangerous, and it can penetrate lots of materials. So make sure that you, if you hear about gamma radiation, get behind some lead or get behind some concrete, because it will go right through the paper, it'll go right through the aluminum foil, but you can be safe behind lead or concrete. So gamma decay occurs when the energy in the nucleus is just rearranged, redistributed. So this often occurs with isotopes. When an isotope changes from a high energy state to a lower energy state, gamma radiation is given off. And when we have extra energy, we represent that as a little asterisk, little star. So let's look at an example. A good example here would be 257 and 104 RF star. This is Rutherfordium, and this is going to undergo gamma decay, and so it's going to go to a lower energy isotope plus a gamma particle. So here again, the star just means that it has extra energy. I just like to write E for energy. So it's not going to change its mass number. It's not going to change its atomic number. And it's not going to change its symbol. We just get rid of the extra energy that was sitting in the nucleus as it redistributes itself. All right, we are going to practice this lots tomorrow because I know that this kind of thing takes a little bit to sink in. So please write a list of all your questions and we will go over them tomorrow in class.